Hey, what's up? This is your old pal, Mr. Cook. We just got through the first problem. Now we're going to do number two. Let's see what we got to do here. So now we're given the graph of the derivative. So we just previously did, use the same exact graph, but we were looking at the original function f of x, so the function itself. Now we're looking at its derivative. So that means that this y-axis, all of the y values that I get from every one of these coordinates are going to be derivatives. So I need to be thinking of it, through that lens. I'm looking at the derivatives when I look at the y values, okay? So like, for example, if I were to take like this point right here, okay, let me tell you everything I know about this point right there on this graph. I know that for whatever that x value is, okay, whatever it is, it's some negative value, my y value is equal to the derivative of that x value, okay? And since it's above the x-axis, that means that the y value is positive, so that means that the derivative is positive. And if the derivative is positive, I'm trained to know that if the derivative is positive, this means that the graph, the original graph, f of x, which is not graphed here. We don't know what the graph of f of x looks like, but we do know that it's going to be increasing at that point. And why do we know that? It's because at that particular coordinate, this coordinate that I've just talked about right there, the derivative is greater than 0. Okay, the y value, the derivative, is greater than 0. And that's what I know about it, okay? Another thing is that at that point, I can talk a little bit about what's happening with the second derivative as well. Because remember that the second derivative is quite literally the derivative of the derivative, okay? So whatever analysis that I used in the previous problem that talked about the derivative, for those first couple points, the critical points and the intervals where it's increasing and decreasing, those same thoughts that cross my mind about increasing and decreasing are going to be applied to the second derivative, okay? So at that point right there, the graph is going down and to the right. That means that the derivative at that point is negative. So the derivative of the derivative is the second derivative. So at this point, the second derivative is decreasing. The first derivative is decreasing. So the second derivative is going to be less than 0 or negative. So at this particular point that I've highlighted, this is going to be concave down. Okay? That's like all I know about it. It's increasing and it's concave down at that particular point. I don't even know what the point, the actual value is on this. I just know that it's above the x-axis. That tells me that it's going to be increasing. And then it's also, the graph itself is decreasing. The derivative graph is decreasing. So that means that the derivative of the derivative is going to be negative. Therefore, the second derivative is negative, and the original function is concave down. I hope that made sense. I hope that's not just a word jumble, but let's go through this problem and hopefully, as we're going through it, if some of this isn't making sense, it starts to make a little bit more sense. Okay, so let's do our work on this. So we need to find the critical points for x for the original function. So the critical points that I'm talking about are in regard to f of x. Okay. So how would I find out where the critical values are, the critical points are for f of x? So what I would do is I would take its derivative, right? And I'd set it equal to 0. And I'd also check the derivative and see if there are any x values that lead to the derivative not existing at that point. So what does that mean? If the derivative is equal to 0, okay, if I translate that over to this graph, remember that the y-axis is the derivative values. So where is, on the y-axis, the 0? So it looks like it would be like right over here, along the x-axis. So the x-axis, when you're graphing out the derivative, the x-axis is where the derivative is equal to 0. Okay, so that's when the graph is of the derivative. Okay, so this is real important to know. All right, so f of x equal to 0 is any point that is an x-intercept. So this part of it, where I'm looking for these critical values, one place that I can look is just on the x-axis. So if I have any points that are there, and it looks like I've got a bunch, those are all going to be considered critical points. All right, so I've got my first group of critical points. X is equal to, it looks like, -2 and 0 and 2 and 4. Those are all of my critical points that have a derivative equal to 0. But remember, there's another part of this, right? So I can also find a critical point if the derivative has some kind of situation where the derivative doesn't exist, right? That's another place where I have a critical value. And the way that that might look would be something like this. Like if I had a vertical asymptote on this graph, okay? So like something like that. That's a place where the graph wouldn't exist, okay? So I'd like look at that x value, whatever it is, and say, hey, that's also a critical number. But I don't have that situation, so we're all good. It looks like those are the only critical numbers that are going to matter on this graph. Okay, so there's our critical numbers. Now let's find the intervals where the graph is going to be increasing or decreasing. And I'm not talking about this graph, the derivative graph. I'm talking about the other graph. And this thing is not even pictured. We don't know what it looks like. But the derivative graph is going to help us to determine where this graph is increasing or decreasing, okay? So let's try to think our way through this. Well, previously, we realized that the way that we can tell if the graph is increasing or decreasing, the original function, if it's increasing, I know that the following will be true. I'll know that the derivative of that graph or the derivative of that function is going to be positive. It's going to be greater than 0. So let's translate that into the graph that we have. Well, if the derivative is greater than 0, it's positive. Remember that our y values are the derivatives. So this means that the y values are positive on this graph. And where are the y values positive? That's going to be the points that are above the x-axis. So all of these points here are going to have derivatives that are more than 0. In other words, places where the graph is increasing, where the derivative is positive. And same thing over here. At these two spots on the graph, it's where the graph is above the x-axis when we're graphing the derivative, okay, the derivative function. Okay, so this gives us two intervals where the graph is increasing, and it looks like it goes from -2 all the way over to 0. So that's one interval where it's increasing. And then another interval where it's increasing starts at 4 and it keeps going on and on forever on the x-axis. So 4 to infinity is the other place where it's going to be increasing. And remember, I'm not talking about this graph being, increasing. I'm talking about the original function that I don't even know what it looks like, but I know that it's going to be increasing over those intervals. Obviously, now we're going to get into the parts where it's decreasing. So when the original graph f of x is decreasing, we know that the derivative of the function is going to be less than 0. That's what decreasing means. And if the derivative is the same thing as y on this graph that we have graphed in front of us, that means that y is less than 0. The only place where y is less than 0 is when it's like below the x-axis. So I'm talking about like this spot right here. This is where the derivative is less than 0. Same thing here. It's below the x-axis, so it's negative. It's less than 0. Same thing here. All of these are below the x-axis. So all of those intervals that I have listed off are going to be where the graph is decreasing. So I can write decreasing for this, and then just write out the graphs. So going from -infinity all the way up to -2. And then also from 0 all the way up until we get to 2, that critical number. And then going from 2 all the way until we get to 4. That's also an interval of decrease. And then I would just group them together with unions, just like I do with the intervals that are separate. Okay, so that's where the graph is increasing or decreasing when I have the graph of the derivative in front of me. I don't know what the original function looks like. All right, now let's take a look at the intervals where it's concave up, concave down, and then also inflection points. I'm going to erase all this stuff. It's not really necessary right now at this moment. It will be in a second, and that's okay. I can reference it when we need it. Okay, the next part is going to be about concavity. So just like before, I'm going to break from the ordering of this a little bit, and I'm going to do intervals where it's concave up and concave down first. So when I wanted to know if the original function was concave up, here's what I would do. I would take the second derivative, and I would see where the graph is greater than 0. So what does that mean for the graph that we currently have, this graph of the derivative of the function? Well, let's try and get this derivative to turn into the second derivative. The way that we do that is we would take the first derivative and we would take its derivative. So I'm going to try and think about, when I'm thinking about concavity and stuff, I'm going to think about the derivative of this graph. So the derivative of this graph would be positive if the graph is increasing. Okay, so I'm looking for where this graph, the derivative graph, is increasing. Because if I can tell where there are intervals where it's going to increase, this tells me where the second derivative is going to be positive, and that's going to be concave up. Okay, so increasing first derivative graph means that the original function is concave up. Okay, well, let me rewrite that a little bit so it makes a little more sense. The second derivative is greater than 0, and therefore the original function is concave up. All right, so let's figure out what that is. So where is this graph increasing, going up and to the right? It looks like that would be like right here. It's going up and to the right for sure there. So this interval would be where it would be, the original function is concave up. And then another interval where it's increasing right here, going up and to the right. That'd be another spot where the original graph is concave up. And then it looks like I've got one more interval where it's increasing from here to here. And that's the last interval where the graph is going to be concave up. Okay, so let's go ahead and write all that up there. Let me get some space. I guess I could do it right here. All right, so concave up. So it happens on the following intervals, going from negative infinity all the way up until -1. It's concave up. And then going from 1 to 2, it's concave up. And then going from 3 to 5, it looks like it's concave up. So all those intervals. And then I combine them together with a union. All right, concave down is going to be the other stuff because it's decreasing. So if the derivative graph is decreasing, then its derivative is negative. And if the second derivative is negative, it means that the original function is concave down. So just to put that into perspective, if the derivative is decreasing, that means that its derivative is negative, so less than 0. And if the second derivative is less than 0, that means that the original function is concave down. Okay? So these are the intervals where it's decreasing, where the derivative graph is decreasing. So that means that the original graph is going to be concave down. So it looks like that's going to go from -1 to 1, and then from 2 to 3, and then finally from 5 to infinity. And then I group them together with unions, and that's where this graph is going to be concave down. Okay. Now let's go ahead and do the inflection points. So the inflection points, remember, those happen where you change concavity. So going from concave up to concave down, or concave down to concave up. So it looks like I've got an inflection point like right there. So at -1. And then also another one that changes concavity right here, going from decrease to increase. So at 1. And then I've got another one like right there, where it changes from concave up to concave down. So that's going to be at 2. And then another one right here at 3. We got a lot of inflection points. Then another one right there at 5. So those are all my inflection points, where it goes from concave up to concave down, or concave down to concave up. Okay, let me go ahead and erase all this stuff, and let's do the last part, the relative maxima. But you know what? Let's do the same thing as before. Let's find relative extrema. Okay, so minimums or maximums. All right. So the way that we do that with the derivative graph is as follows. We first find the critical values, which we already have, and we can put them on a number line if we want. So we've got -2. So I'm just taking from this list here. -2, and then 0, and then 2, and then 4. Those are all our critical numbers. And then from that, we broke it up into intervals where it's going to be either increasing or decreasing. So we went from -infinity to -2, and On that one, we said that since below the axis, it's going to be decreasing. And then the other one was from -2 to 0. And then on that interval, it's above the x-axis, so we're saying that it's going to be increasing. And then let's see, from 0 to 2 is below the x-axis, so that's going to be decreasing. And then also from 2 to 4, it's below the x-axis, so that's decreasing as well. And then it's above the x-axis from then on, so from 4 to infinity, increasing. All right, so how does this translate to finding our relative extrema? Well, these critical numbers are potentially going to be either relative maximum or relative minimum. So let's change that to relative extrema. There we go. All right, and then let's just list off what happens with each of these. When x is equal to -2. Well, the graph is going to go from, now this is what I'm talking about with the original graph. This is kind of like a basic understanding of what it's going to look like. It's going to be decreasing, so going down and to the right until it gets to -2, and then it's going to be increasing because it goes from decreasing to increasing at -2. So if this is the actual graph, f of x, I know that at -2 I'm going to have a relative minimum. Okay, let's see what happens at 0. So when x is equal to 0, it goes from increasing, which is going to be going up and to the right. Then it gets to 0, then it's decreasing, so it's going to be going down to the right. So that looks like it's going to be at the top of the hill, so this thing is going to be a maximum at 0. So that's a relative maximum. Okay, let's see what happens at x equals 2. So it's going to be decreasing, and then all of a sudden it's going to be decreasing again. So this is a spot where it's neither a maximum nor a minimum, so we don't say that it's a relative max or a relative min for that reason. Okay, and then we have an instance where we've got decreasing and then increasing. So the only way that that happens is if like that value 4 is going to be a minimum. So at x equals 4, that's going to be a relative minimum as well. Okay, so that really explores like the difference between the first derivative graph and the original function graph. So, you know, just if you have questions, make sure you ask us. I hope this was helpful. That's the end of this video, and we'll see you in the next one. Bye-bye.